All right, let's dive in. Today, we are tackling one of the most incredible fundamental forces in our universe, electricity. I mean, it's everywhere, right? It's in the phone you're holding, the lights in your room, even inside your own brain. It literally powers our world. So you've got to wonder, how does it actually work? Let's find out.
Have you ever really thought about it? You flick a little plastic switch on the wall and boom, instantly the whole room is filled with light. It feels like magic, doesn't it? But it's not. It's just pure, awesome physics. To understand how that instantaneous change happens, we need to zoom in. Way, way in.
So the whole story of electricity really starts with one single idea: electric charge. It's a basic property of matter, kind of like mass. And the hero of our story, the tiny particle that makes it all happen, is one you've definitely heard of: the electron.
Okay, you have totally done this before. Ever rub a balloon on your hair and stick it to the wall? That's exactly what's happening here. When you rub these two materials together, the friction literally scrapes tiny electrons off the cloth and sticks them onto the plastic rod. That simple little transfer, that's static electricity right there.
And this leads us to two kinds of charge. Pretty simple, right? The object that lost electrons now has more positive bits, protons, than negative electrons. So we say it has a net positive charge. And the object that gained all those extra electrons, well, it now has a surplus, giving it a net negative charge. It all comes down to who has more electrons.
So now we've got these charged objects. How do they actually interact with each other? Well, lucky for us, there's a rule book for that. It's called Coulomb's law, and it's a huge deal in physics. It tells us exactly how charged particles either push or pull on each other.
And the number one rule in that rule book is incredibly simple, something you've probably heard your whole life. Opposites attract. A positive and a negative charge will pull toward each other, and like charges, they repel. Two positives or two negatives will push each other away. That's it. That's the fundamental rule that drives everything else.
So just how strong is that push or pull? This formula gives us the answer. Now don't worry about all the letters. The most important part to look at is the r on the bottom. That's the distance between the charges. Because it's squared, the force gets weaker really fast as you pull the charges apart. If you double the distance between them, the force drops all the way down to 1/4 of what it was. It's a huge drop-off.
Okay, but wait a second. This brings up a really cool question. How do these charges know the other one is there? They aren't actually touching, but they're still pushing and pulling. The answer is something amazing called an electric field. So get this, every single charged particle creates this invisible zone of influence all around itself. You can kind of picture it like an invisible spider's web radiating out in all directions. When another charge wanders into that web, into that field, it suddenly feels a force. The field is the thing that carries the message from one charge to the other.
And this is what those fields look like. The way we draw these lines is by imagining what would happen to a tiny positive charge. So around the positive charge on the left, the lines point outwards because it would get pushed away. And for the negative charge on the right, the lines point inwards because our little positive charge would be pulled right in. And we can even measure the strength of that field anywhere in space. The electric field E is basically a map of potential force. It tells us, hey, if you put a charge Q right here, this is how much force F it's going to feel. It's like a way of describing the force that's just waiting to happen.
Okay, so far we've only been talking about charges that are just sitting still, static. But here's where the real magic begins, the part that actually lights up our world. It happens when we get those charges to move. When charges start to flow, we call that an electric current. And that's what we actually use to power things.
Now, to really get this flow, you need to know about 3 key players. The easiest way is to think about water in a hose. Voltage is like the water pressure from the tap. It's the push that gets everything moving. Current is the actual amount of water flowing through the hose. And resistance? That's like putting a kink in the hose, making it harder for the water to get through.
Now these three things, the push, the flow, and the obstacle, they're not independent. They are all linked together by one of the most important and, thankfully, one of the simplest laws in all the physics.
And this is it. Ohm's law. Voltage equals current times resistance. Seriously, this little formula is the golden rule for so many electrical circuits. If you know 2 of these things, you can always figure out the third. It's the fundamental rule of the road for electricity on the move.
So now that we have our charges moving and we have the rule book for how they behave, we can actually start to build stuff. And what we build is called a circuit. A circuit is really just a closed loop, a complete path that lets the current flow from a power source through whatever we want to power and then back home again.
When you start connecting things in a circuit, you basically have two main options. You can connect them in series, which is like a one-way street. The current has only one single path to follow through everything. Or you can connect them in parallel, which is more like a fork in the road, giving the current multiple paths to choose from.
And you can see that difference perfectly right here. On the left, that series circuit is one single loop. The current has no choice but to go through both components. But on the right, in the parallel circuit, the path splits. The current can go down one branch or the other.
So for series circuits, the rules are pretty straightforward. Since there's only one path, the current has to be the same everywhere. The voltage, though, the push, gets shared or divided up among the components. And the total resistance? Easy, you just add them all up.
Now, parallel circuits kind of flip the script. In this case, each path gets the full voltage from the source, no sharing. But the current has to split up to go down the different paths. And here's a wild little quirk. Adding more paths in parallel actually lowers the total resistance, making it easier for the current to flow overall.
Okay, so we know how to make charge and how to make it flow. But what if we want to, save some of that electrical energy for later, like a little electrical battery pack? For that, we need a very special component.
Let me introduce you to the capacitor. The simplest version is just two metal plates with a small gap between them. When you connect it to a battery, positive charge piles up on one plate and negative charge on the other. This creates a strong electric field in the gap, and bam, you stored energy.
And this ability to store charge has a name: capacitance. You can think of it like the size of a water bucket. A bigger capacitance, C, means the component can hold more charge, Q, for the same amount of voltage pressure, V. The bigger the bucket, the more charge it can hold.
And there you have it. Look at the journey we just took. We went from understanding a single, stationary electron and the invisible field around it, all the way to getting billions of them moving in a controlled flow through circuits that can power things, and even store energy for later.
And that's really the big takeaway here. All of these fundamental principles, from the simple pull between two charges to the rules of a complex circuit, they aren't just textbook ideas. They are the absolute building blocks of our entire modern world. Every phone, every satellite, every EV, it all runs on these same basic rules, which just leaves one final, really exciting question. Now that we know the rules, what incredible future will these tiny sparks power next?